Hello everyone, welcome to our exhibit for EOH 2021. I am Samya from the Ewoldt Research Group in the Department of Mechanical Science and Engineering, and our exhibit is called the Rheology Zoo, where we study fluids, solids and things in between. Now what I mean by that is there are things that are not always purely liquid or purely solid like. So there can be behaviors that sort of in between. Now I'll get to what I mean by that. But let's set some background for what a liquid is. So this is water. Now is this a liquid or a solid? Well, of course it's a liquid because it sloshes around in its container. It hasn't got its own shape, so it takes the shape of the container that it's in. So it's a liquid. It's got a flat surface. If I stir it up, it doesn't trap any bubbles and all the bubbles escape very soon. So it's a liquid. Now this is a pebble or a rock. Now is this a liquid or a solid? Of course we know it's a solid because it's hard, it's got its own definite shape, it cannot be deformed easily. So this is a solid. Now this is a container full of sand. Would you call this a liquid or a solid? See, this is a trick question. It might seem the sand is a solid because of course it's made of many small particles or grains of sand which are solids themselves, because you can think of this pebble, make the size pretty small, say less than a millimeter or 1/10 of a millimeter, and put many of those in a container and you would get sand, which is presumably a solid. But think about what you answered for water as to why it was a liquid. Sand too sloshes around. If I shake it well enough, it's got a flat surface at the top, it takes the shape of the container and it flows pretty easily. So by that definition it might actually be a liquid. So it sounds a bit odd that a collection of solids can give you a liquid, but this is what is related to the idea of things being in between a liquid and a solid. Next we have something called jelly bath or squishy bath. This is like a bath time toy for kids where you spray some powder in your bathtub water and then you get a sort of gooey substance. So this again looks like a liquid, right? It takes the shape of its container, it flows around easily, but if you notice carefully, you'll see that there are many small particles which are now sliding down the walls of the container. So this is a liquid made up of solids. So you take many solids, disperse it in liquid, and well, you can have a liquid made up of solids. Now you can see these particles because they are millimetric in size. But if you make these particles small, say microscopic, so that you cannot see them with your naked eye, then you get something called, in this case, it's like a gel. So it's a homogeneous substance. This is hand sanitizer, by the way. So we all use this, we all know what this is. So is hand sanitizer a liquid or a solid? Well, it takes the shape of its container, it's flowing around pretty easily, so you would think it's a liquid, right? Well, of course, but think again. Look at the surface of this. Is it flat? It's not flat, right? It's slanted. So it's got solid-like characteristics. Plus if I shake it up, you'll see this big air bubble over here. It's trapped, it's not rising, it's not escaping. So that's a solid-like behavior. So this is something in between. This is neither a fluid nor a solid, and it depends on the conditions. So this is the first key phenomenon of rheology for studying these weird in-between like substances. This is called shear thinning. The first key phenomenon is called shear thinning, where a substance can behave like a liquid or a solid depending on how hard you push on it. This is a solid unless you disturb it too much, and beyond a certain amount of applied stress or disturbance, it flows, sloshes around, takes the shape of the container and behaves like a liquid. So that's the first key phenomenon of rheology. It's called shear thinning. This is called a yield stress fluid. Next, the second key phenomenon of rheology. So these yield stress fluids behave like liquids or solids depending on how hard you push at them. Viscoelastic fluids or solids behave like fluids or solids depending on how quickly you push at them. So this is silly putty or therapy putty. As you can see, this looks like it has flowed and taken the shape of the container. It's filled the entire volume at the bottom, which is great, but oh, it doesn't drop out, so it must be a solid, right? Yeah, technically you're right, because if I punch it, I'll hurt my knuckles because it's pretty hard, it's solid-like. But these behave like solids or liquid depending on time scales, how hard I hit it. If I hit it fast, it behaves like a solid. But if I keep my finger and I keep pressing it slowly, you'll see my finger starting to go in. So I'm able to create a dent in the supposed hard solid, because if I wait long enough, if I apply a stress and wait long enough, it can actually behave like a liquid. So these materials are called viscoelastic. See, I made a dent. These are viscous or fluid-like and elastic or solid-like, depending on how fast of a deformation is applied to it, whether I'm deforming it quickly or if I'm deforming it slowly. Now these materials, the viscoelasticity in these can be demonstrated using something else, which we like to call happy and sad balls. So this is two rubber balls which are well indistinguishable otherwise, but one of them is more viscous, one of them is more elastic, which is one of them is more dissipative or liquid-like, whereas the other one stores energy, so it's more solid-like or elastic. Happy and sad balls, two otherwise identical rubber balls, one which is more viscous, one which is more elastic. So can you guess which one will bounce higher if I drop them from a height? This guy's sad, doesn't bounce, this guy's happy, he bounces. So this is said to be more elastic because it bounces and it stores energy, dissipates energy, stores, dissipates. So it's elastic. This is more viscous because it doesn't store energy, it dissipates all the energy that you give to it. So this is more fluid-like or viscous or dissipative. This is more solid-like or it stores energy. Although both of them are viscoelastic, this has both characteristics of viscous and elastic, whereas this is also viscous and elastic, but this is more viscous, this is more elastic. So these both are viscoelastic, and viscoelasticity is the second key phenomenon of rheology. Alright, now let's move on to our third key phenomenon of rheology, which I like to call self-siphoning or extensional thickening. Now, before that, I would like to show you two containers of water. What I'll do is I'll pour water from one container to the other. Notice the upper container. I'm tilting it and I'm pouring it, but the moment I stop tilting or I tilt back, the fluid stops pouring. So it's what you expect, right? It's what you expect water as a liquid to do. Done. But if I do the same with a different substance, these are PEO solutions, 1 weight %. So it's 1 gram of something called a polymer that dissolved in 99 grams of water. So it's a very small amount. But I'll try pouring this into this. These both are liquid, as you can see. They're sloshing around. They are flowing. Their surfaces are flat. So these are liquids. But notice the top beaker. As I'm pouring it, it has started pouring over, right? But now I go back. But you see, it's still pouring itself out. So this is called the third key phenomenon of rheology, which is extensional thickening or self-siphoning, is that the fluid siphons itself. It pours itself out despite the fact that, well, I stopped pouring it. And the threads keep coming and they actually don't stop. So this is again not very fluid-like behavior. It's weird. It's as if it's a solid that's continuous work but very easily deformable and flows, well, kind of continuously. So yeah, it doesn't break up like you expect a fluid to break up. So it forms in long threads, and that is by virtue of being a polymeric solution. Now for the fourth and the final key phenomenon of rheology, I am showing two fluids, both water, being stirred by two stir rods. This is pure water, but this is again a solution of PEO polymers just added with a bit of fruit coloring to make it look different. So this is polymeric solution, this is pure water. So keep an eye on what happens to the water when you start stirring it. What do you expect? A vortex, right? The fluid sinks at the bottom, rises at the top. This is what you would expect if you stir a fluid, say in a bucket, right? So this is normal. Now if I do the same with water, except that it has a bit of polymer added to it, you see what happens now. Ooh, that wasn't expected. So the fluid started rising in the middle and sinking at the edges. So these two behaviors are completely opposite of each other. This is because of the added polymers to it that makes the fluid stretchy and non-Newtonian. So this is called the fourth key phenomenon of rheology. It's called rod climbing or Weisenberg effect. Alright, so that was it from our side. I'll summarize the four key phenomena of rheology: shear thinning, viscoelasticity, extensional thickening or self-siphoning, and rod climbing or the Weisenberg effect. These are four interesting things that we observe, that we study in our group for analyzing the mechanical or material behavior of substances that are neither solid or fluid-like because they are in between. These challenge the